Hi, James. How's it going?
Okay, so I think one of the reasons why they really want to do notes today was when you look back in the year, this is going to be one of the harder sections that we do. People tend to have more difficult time. Okay, yes, you forgot. So volume, we're going to talk about volume today, and we're just doing the one section. There's actually two methods to find volume. There's 6.3 and then there's another method in 6.4. Unfortunately, 6.4, that's not on the AP exam, and considering the limited amount of time we may or not get to it, it would be on in most calc classes for sure, but we're going to try to just focus on what we need to do for the test here to get through everything. So, page 455, 6.3 volume. We're going to start with an example, or walk through an example to help us understand exactly what's going on here. So it's very similar to area. You're going to be given equations to define a space or an area. So let's say, for example, we have y equals x squared, and then x equals 2, and then y equals 0. So we have all of those equations. I'm going to graph them. Y equals x squared is a parabola. It looks like this. X equals 2 would be this straight line here. And of course, y equals 0 would be the x-axis. So the very first thing is you should shade in the region that we are talking about, that was defined by all those graphs. And then they will ask you to take that two-dimensional figure and rotate it around an axis. So in this problem, we're going to rotate about the x-axis. So in other words, I want to take that shape and rotate it around the axis. And I have some little models here to try to help you see what's going on. So this isn't exactly the same shape, as you can tell. Kind of looks like a boot here. But if I hold it up, we're going to take this shape, we're going to rotate it around, and as you rotate it around, you are creating a three-dimensional shape. Okay? And so when you're done, you get this solid that looks like that.
What is a thing?
This is a bell. I don't know if it came from a... This actually has quite the sentimental value to me. I don't know if this came from a 4th of July celebration, or sometimes people have, like, well, a long time ago, wedding decorations, wedding bells. I have no idea. Mr. Rome, who was for a long time the only math teacher for a long time at VHS, back when they only needed one teacher to teach all the math, every student math, and he taught most of the science too, including physics. And the high school was the K-wing. That was the whole high school. Anyway, he taught calculus for several years, and when I came aboard, my second year, he asked me to take over the calculus program because he knew he was going to retire the following year. So then I inherited all of his little toys here. So, but anyway, get the idea? Three-dimensional shape?
Yes.
Okay, you need to draw this on your paper. So you would want to, the first thing I would suggest is to draw the reflection. So reflection going across this x-axis. And then you can draw in some lines here to indicate that we have this three-dimensional shape. So the bottom, of course, this would be the bottom here, and that would be circular. Kind of looks like a Hershey's Kiss laying on its side. Yeah. Or pointed that direction. Pardon me?
What's your little arrow at the top indicating?
This side is I think of that as the bottom. Like this flat side here is the bottom, so it looked like this. Another way to think about it, if you've been in any kind of tech ed classes and you've seen a lathe before, so like woodworking or even metal lathes. So if you're in manufacturing, you become an engineer, you design parts, and you create, like a baseball bat, for example. You might not realize, there you go. Yeah, so that baseball bat you just happened to bring with you today.
I made it on the lathe right before this.
That is unbelievable. wish we could get this on videotape here. Nobody's gonna actually see your beautiful bat. Look at that thing. How did you make it?
So you just put a block of wood.
Solid block, like a rectangular solid, right?
Yeah,
or whatever you
octagon,
get.
Actually.
Yeah, okay, perfect.
And then you spin it.
So you stick it in here and it spins super fast?
Yeah, and then you take a metal knife kind of thing and you just chip away at it.
Perfect. And you have these little blades and they just slowly carve away. That's exactly it. That's how they make baseball bats. Make a lot of manufactured parts. Everything that would be circular. You know what I'm saying? Spin it around. So that's the same idea. We're going to rotate it around. We're going to create a three-dimensional object.
That is so
Man, it doesn't work out any better.
Well, I could have had a clay pot.
Yeah, the same idea, right? With a clay pot, you know what I'm saying? Perfect. So, now that you can visualize what we're talking about here, I want you, the next thing we're going to do is talk about the theory behind what we're going to do. Okay? So, here is our shape. Pretend this is a ham. Alright, anybody here work at Miller's?
Cups.
Hops? Yeah. You've been to Miller's, right?
Yes.
Go up to the deli counter. Nobody works at the deli here? That's my dream someday, to work in the deli. Because when I really want to, maybe they'll just let me play back there one day. I want to use those machines that slice up the ham. You know what I'm talking about?
Yeah.
Yeah.
That
That you
like push back and forth.
Yeah, exactly. So here is a ham. You're going to put it on the ham slicing machine. And you're going to start slicing off pieces of ham. So you're just going to put it in the machine and it goes zoop, zoop, zoop and slices it right down. Okay? On your shape, what that looks like over here is basically you're going to come along here and you're just going to start slicing pieces of ham off. And so here's the theory. If we could find the volume of each slice of ham and add those volumes up, we'd have the volume of the whole piece. Alright? So we're going to focus on one slice. We're going to take one slice off the ham. We're going to lay it on the counter. And what does it look like? It is circular, you bet. Is it just a circle?
No.
It's a three-dimensional shape, right? It is a cylinder. I heard somebody use the word disc, like a
You could just hold it like this.
compact disc. I saw Heather hold up her hands like she was eating a hamburger. Yeah, so it's all the same idea. It is a cylinder. And if you think about, probably the best way to think about it is, you guys know what a CD is? You guys don't use CDs anymore? They came out right after cassette tapes. I don't know if they, all right. Well, they came out right after 8-track tapes, but that's a whole other story.
I actually don't know what day. Yeah, I don't know what an 8-track tape.
When I was a kid, we had a big, huge stereos like the size of this table with it was wood, and you lift up the top, like everybody had them. It was like the fancy, and it had an 8-track player in it. They're like, they almost look like a box that a movie would come in, but they were thicker, and you just stuck them
So
in,
like
and
VHS?
you got like 6. Yeah, it was different. I don't know. It's kind of hard to. It's probably worth a lot of money, and we didn't throw it out in the garbage one time. But anyway, that was. But anyway, all right. I can digress. Here we don't have much time. We got to get back. So, think of this as a disc. So somebody said disc method. This is a disc. They call this the disc method. The book spells disc with a K. Some professors like to do that. That's fine. And of course, some professors or some people now, because CD, compact disc, is usually spelled with a C, they'll spell that. It doesn't really matter how you spell disc. Okay? Just be aware of that. So then we have this. We have a disc. We have a cylinder. We want to find the volume of one slice. Volume of one piece of ham. How would you find the volume of one slice of ham? Volume of a cylinder is pi r squared times the height. Perfect. Well, for our slice of ham, this is the height right here. And if you go back to the drawing, the width of this, that's the height. And what do we call the width of these slices? Delta x. Tony, you had a question? Yep.
Is this assuming that like these slices are so small that the two like sides are the same, the two bases are the same area?
All right, I'm glad you asked that. Yeah, it's just like when we did the Riemann sums. It's the same issue. It's not. This is an approximation, right? Because you got these little triangles. Like if you know, we're talking about the tops being flat. So there's like this little piece of triangle. Maybe that's just the fat. And you don't really care about that. I don't know. But that's the idea that this is approximation. How can we go from an approximation to the exact value? What should be happening to our slices of ham? Yeah, they should be. So that's the cool thing about that slice machine. You can dial in exactly how thin you want the. You know, some people like their ham thinner than others, but you want the thickness of your ham. You want it to approach 0. You want delta x to approach 0. Okay. So in our little formula here for one slice, the volume for one slice is pi r squared times delta x. That's one slice. The total volume, how do we add up all the slices? How do we add up all the boxes for area? What would we do?
Oh, I just had a question.
Yeah.
Is HT, is it just height or is...
That's the height of this. The height of our cylinder. How do we add up all the boxes when we did area? The sum. We want to take the sum of all these boxes as delta x approaches 0. That is the definition of the integral. That's what it's all about. Okay, so it's the integral that's going to add up all of these slices, these discs, and instead of using delta x, we use integral notation, we use dx. This is it. This is the volume formula. This is the disk method again. Okay, that's the equation right there for the volume of a three-dimensional shape using the disk method.
So delta x just turns into dx then?
Exactly. In terms of a notation standpoint, it was the same way when we did those Riemann sums. If you remember, it was f of x times delta x, and the integral is the sum. That's why it looks like this long skinny s, the integral symbol. And delta x, we end up using dx for the representation of that. Yeah?
Is that still just the volume of the disk or of the entire thing?
Once you add up all of it, it's the integral, it adds up all the pieces. It's the sum of all those pieces as delta x approaches 0. It's the exact volume.
And then does the radius just end up being the distance from the line to your x line whenever you rotate it around?
Great question. And that's the hardest part, to find the radius. And we're going to walk through several examples doing that. This particular problem, yes, it would be from the function down there. But that's not always the case. It depends on the picture. So let's talk about that right now. We have to have limits a to b. So let's go back to our drawing here, our problem, and see what we're talking about. This is a dx problem. So limits. Always look at the original shape. Not the whole thing after you're done revolving, but if you're having trouble with limits, look at the original shape. What are the x values from the beginning to the end of that shape? 0 to 2. So those are my limits. The pi is a little brother. We can just put that out front. We need r squared. So now we got to find out what the radius is. So draw a picture. I have no idea how you're going to be able to do these without a picture. Come here, we look, this is the center, this axis of rotation, that's the center of all of our discs, all of our slices of ham. Then we go from here out to the outside of the ham. This is R right here. Well, how do you find how long something is? You would subtract. It's just like you did with the boxes. I want to find out the length from here to here. That's R. So I'm going to take top minus bottom. So R equals whatever the top minus bottom is for this problem, because that's the direction we're going, top minus bottom. Well, the top happens to be changing. It follows along this function, so the top is just the equation x squared. And what's the bottom here, do you notice? 0. Will it always be 0? You would like to think so, but no. If it's going around an axis like it is here, it's 0. This is the equation. The x-axis is y equals 0. But you'll be asked to revolve things around different lines, like y equals -5 or x equals 2. Okay, so it's not always 0. The radius won't always be just the function as it is in this problem. You really need to look at the picture and think top minus bottom, or if you're going the other way, right minus left. Alright, and we'll do some of those examples so you can see exactly how that's working out. So, but for this one, the radius is x squared. Don't forget to square it, and then dx. So you would continue on. You would have pi.
So this is similar to the equation with like arc length?
In what way?
And like since you said don't forget to square it.
Only because it's r squared.
Oh, okay.
Yeah, and there was a square in that formula too, but that's completely different because it was a derivative. So you would get 1/5 times pi x to the 5th. Plug in the 2. Plug in the 0. 2 to the 5th is 32, so 32 over 5 pi. And plug in 0, you get 0. That's the exact volume of that little sideways Hershey's Kiss or chunk of ham. If you don't like, some people don't like ham, they can't eat ham, or then I don't know, turkey or salami or tofu, whatever you want. But that's the idea. Or avocado. This works for avocados. We did a lab once. I brought in avocados. Got kind of messy though, because if you don't cut avocados right away when they're cold, they kind of get mushy. But anyway, you get the idea? Exact volume, no approximation. Think about that. Up till now, you could only find the volume of perfect geometric solids, so spheres and boxes and things like that. Now you can find the volume of anything. We could find the volume of that baseball bat if we knew the function that defined it. And that's what engineers do when they're designing and building something. They will create a model for it based on some sort of equations, and they can tell you exactly what the volume is. And if you knew the density of the material, you could find the exact weight, and that might be extremely helpful to an engineer to be able to do that. Or somebody that's in an engineer that's in designing parts and things like that. Yeah.
Doesn't it only work for things that are symmetrical though?
Well, in this case, we've only talked about things that are being rotated, right? We're going to talk about other shapes too before we're done here today. But for right now, we're going to focus on those that are being rotated. Good question. All right, let's do another example. So now we're going to go y equals 4 minus x squared. And just in the first quadrant, basically another way of saying x equals 0, y equals 0. And we're going to rotate that now about the y-axis. So rotate about y-axis. So we would draw it out, sketch this. So you get 1, 2, 3, 4. And the first quadrant, so here's your, goes like this, not really drawn to scale. You get the idea. So here's my original shape, that's all in the first quadrant. We're going to rotate it around the y-axis this time. So I have another model for this one. So you think this is similar, pretty darn close to that shape right there. Rotate it around. This would look, basically looks like a hemisphere. This one would be a little bit more oblong, maybe more like a bullet, like the tip of a bullet, I would say. I would draw in the reflection, like that. And then you want to indicate that it's a three-dimensional object. Like that. Okay. So it's different because you're going around the y-axis. Here's the advice to help you know which way to cut, which way to slice it. You're going to take this is your ham, you're going to put it on the ham slicer, you got to know which way to cut it so you get circles. So you want to always cut through the axis of rotation. Okay, always cut through the axis of rotation. So it's going around the y-axis, we're going to cut through the y-axis, we're going to end up with slices that go like that. This time, same story here though, pi, the integral, and we're going to go from, well, let's do it right out here. So from a to b of r squared. Since you're cutting through the y-axis, the thickness of these slices now would be dy. So whatever axis you cut through, that determines if it's dy or dx. Okay, so since you're cutting through the y-axis, that's why we have a dy problem. Everything needs to be in terms of y, including your limits. So we're going to go volume, pi, limits. What are the y values from the beginning to the end of the original picture, the original shape? 0 to 4. Okay, have to be y values. R, the radius. I'll go back to my drawing. Please make a drawing. It's so important. Don't try to do these in your head. There's the center, that green line. I go out to my original shape. That's my radius right there. This time we're going to do right minus left. Okay, because to find out how long this is, you take the bigger value, the right side minus the left side. So it would be this equation, that's on the right side, and the left side is 0. Well, the equation is 4 minus x squared. But this is a dy problem. I can't have x's in there. I need to take my equation and I want to solve it for x. I get x squared equals 4 minus y. X equals the square root of 4 minus y. That would be my radius then, because that would be the right side minus the left side, which is 0. So r equals the square root of 4 minus y minus 0, or in other words, the square root of 4 minus y. Square root of 4 minus y, and that's the radius. And it's r squared, and then it's dy. Again, hopefully going through the idea, conceptually, we talk about millers and the ham slicing, you understand where the formula is coming from. That it's really just the volume of the cylinder, and pi r squared is the area of the side, the cross section, the base, and dy part is the height or the thickness. I remember when I was learning this in college, they would just throw the formulas at you, and you never really explained, and it was really hard to figure out which formula to use, and how you set it up, and how to find R. Use your drawing, use your picture. That should help you out. Any questions on setting this one up? We're of course not done, but we're done enough here. You'd want to do the whole thing, just so you know, and square that, take the integral, and go from there. Alright, let's get a little fancier here, a bit more difficult. Next example. Y equals x squared plus 4. Y is equal to 2. Those are your two equations. And they tell you basically you want only x values between 1 and 3. So that's like saying another equation, x equals 1 and x equals 3. And it says revolve around the x-axis. So we draw a picture. X squared plus 4. 1, 2, 3, 4. X squared. Voila. Y is 2. Here's 2. 1, 2, 3, 4. You're going to start at 1 and go to 3. So the area enclosed by that, all 4 of those, is that piece right there. And the directions say to revolve around the x-axis. So to do that, I would draw the.
So this one would have like a hole in the middle.
Yeah, it does have a hole, doesn't it?
You'd be shaping donut.
So you spin it around and you have this. It looks like that. You start drawing too many lines, it's hard to see, but you got a hole. So I got another model for this. Okay, here we go. I know it looks odd, it's a roll of toilet paper. This is about as good of a model as you can get for this. I mean, toilet paper doesn't bevel up and down like that. And by the way, if you're wondering why I have a roll of toilet paper in my cupboard, it's just for this one day, okay? I don't have a personal problem or anything else. I don't need any new rumors floating around on Twitter or anything. But okay, so anyway, you get the idea? Think of this as your ham. Maybe there was a bone in the middle of the ham, they pulled the bone out, and now we put it on the ham slicer and we slice it up. If you look at this side, you can see what the cross section is. What are you going to get? Yeah, it's the other place you gotta want to work at, Miller's, right? Right next to the deli, the bakery. Donuts. So we slice through the axis of rotation, just like this. We take one of those slices, lay it on the deli counter. We look at it and we realize it has a hole in it. It's gonna look like this. Has a hole in it. Now, some people like calling this the donut method. Professors usually don't call it the donut method. They look at that and they think, anybody work at Ace Hardware before? Or does? No, never? Anybody? What is that? Hey, you're a tech ed. What is that? What does that look like? Washer. Yeah, washer is a nuts, bolts, washers, not like the thing you wash your clothes in. So that looks like a washer. So we call this the washer method. And now we got to find the volume of one washer, and then we're going to add up all of them using the integral. So, strategy here, how would you find just the washer volume? How would you do that? What do you think, man?
Take the total minus the inner.
You must subtract the hole out, right? Yeah, so find the volume as if it didn't have a hole, and then subtract off the volume of the hole, which is also a cylinder. So, when you look at that, here's the center right here, let's say. So from the center to the very outside of the shape, that would be that distance. We're going to call that radius big R. So the volume of the entire, you know what else it looks like? Everybody ever get the pineapple rings in the can? Yeah, that's what I was getting hungry again. But anyway, so that's the idea. So the whole thing, well, pi times big R squared. The thickness is still delta x for this problem. So delta x, that would be the entire thing, not counting the hole, I mean just ignoring the hole, minus the hole. So the hole, we got a radius for that also. So that, going from your center to whatever this is here, we'll call that radius little r. So then it would be the volume of the hole is pi little r squared delta x. This is one washer, or one donut, one slice of pineapple. And it's the integral that adds them all up. Now before we throw in the integral symbol here, you can actually do a little bit of simplifying. We can factor, you notice that? Yeah, we can't get rid of it. We can put it out front. So I have delta x in each, and I'm going to actually put the delta x in the back because I know that's going to morph into dx. And I'm going to put the pi in the front. So really it comes down to pi times in parentheses big R squared minus little r squared delta x. Again, that's one slice. So the total volume, and this is the washer method again, would equal the integral of pi a to b big R squared minus little r squared dx. Outside radius squared minus the inside radius squared, the radius of the hole.
You put the pi outside of
Yeah,
it?
can you put
Yep,
it
and the
outside?
pi is the little brother, so you can definitely stick the pi out front. Let's do this particular example. So we have volume is pi, limits, x values for this question. Original shape, just the original piece up there, beginning to the end, what are the x values? Yes, so I'm going to go from, now I got to figure out my radii. So, again, look at the drawing. The outside radius, this axis is the axis of rotation. From there all the way out to the outside, that would be big R. That's a length. You would take top minus bottom for that length. The top is the function 4 plus x squared, or x squared plus 4, that's the top, minus the bottom, which happens to be 0. So big R is just x squared plus 4. Put that in my equation.
Wait, where did it go down to?
It stopped at that axis of rotation, which happens to be the x-axis. So that's the equation y equals 0. So big R would be x squared plus 4. But don't forget to square it. You square these two separately, by the way. Don't square the whole quantity of big R minus little r. And now we have little r. So we go back to our drawing. Little r, that's from the center to the hole, to where the hole ends. It'd be that length right there. This is little r right here. Again, top minus bottom. Well, the top is the equation. What's the equation of the top? 2. And the bottom is 0. So that works out really nice. It's just 2. And you look, yeah, how about that? That never changes. It certainly could, but in this particular example, it doesn't change. It's always 2, so that works out nice. That's my little r. And of course, you've got to square that. So you would FOIL out the x squared plus 4 minus the 4, and keep going from there, and you would find the answer. Alright, so that is new. That's if you have a hole. Now let's get even a little more fancy. Let's go around a line that's not the x or y axis. This is example 4. So I have two functions, f of x and g of x, and it says rotate about y equals -3. So we're going to sketch this out. First of all, drawing those two functions. So this would be a parabola x squared, so this one is going to look like this. And that's also parabola, and that would be so that's going to go like that. So here's my original shape. By the way, it kind of looks like a football there. How do you find out the x values right here, the ends of this football? Yes, set them equal to each other and solve that system equations. For the benefit of time here, I'll tell you you're going to get 1 and -1. That's where they're going to begin and end. And then our axis of rotation is way down at -3. So 1, 2, here's -3. dotted line. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 2 more. Here to there. And it looks like that. And you rotate it, you're going to get this big hole.
It's like a lifesaver.
What do you think it looks like?
Lifesaver.
Yeah, lifesaver. Yeah, because it's kind of curved in there, or it looks a lot like a donut, right? That way. I think of it, it looks like a wedding ring too. You can think of it that way because it's got that really big hole and it's really thin at the top and the bottom. Yeah.
I'm like confused about the drawing. So you go down to like negative.
So this is my axis of rotation at y equals -3. So and then I gotta draw the reflection. So I counted how far away I was from y equals -3, and I did that same distance going down below it. That's how I got that. Is this going to be a dx or dy problem? And how do you know? It's not dy. I'll give you a hint.
Because it's rotating about.
What's the rule?
Parallel to x. If you go across it.
Yes, always cut through the axis of rotation. Cut through the axis of rotation. Here's my axis of rotation. I'm going to cut through it. And do those cuts go through the x-axis or the y-axis? The x-axis. That's what makes it dx. So this is a dx problem. I have a hole, so I got to deal with that. A to b, big R squared minus little r squared dx. All right, limits, x values, beginning to end. I just told you those. Otherwise, you bet. Otherwise, you'd have to find them by finding the points of intersection. Now it gets a little tricky for the r values. Big R, here's the center, the axis of rotation. Go out to the outside, all the way up there. That is big R. To find how long something is, you take top minus bottom. Top minus bottom. The top is this curve function right here, this frowny face, so it's g of x. So 4 minus x squared minus, what's this bottom equation right here? What's the center equation? -3. So it's minus -3. And when you simplify that a little bit, you get 4 minus x squared plus 3. So it ends up being 7 minus x squared. Squared. That's big R. Minus little r. So we come back, go from the center, axis of rotation, to where the hole ends. This space right here. That's little r. Top minus bottom. The top is this quadratic equation, the x squared plus 2. And the bottom is this equation right here, which is still -3. So it's minus -3. And that becomes x squared plus 5. Squared dx. So it can be very confusing. The radii is the hardest part, I think. Look at your picture. Top minus bottom or right minus left. Always go back to that if you're having trouble to figure out how long something is. Now, those are all problems where you're rotating. And for many years, that was it in the world of AP problems in the test. Then one year they threw a problem on there, just freaked everybody out because it said, we're not going to rotate it, it's just a blob sitting there, and you're going to slice it, and you're going to tell me what the volume is. And people panicked and they couldn't do it. So just picture like a chunk of cheese, and you put it on the cheese slicer, you know what I'm saying, and you're done slicing it, and you're supposed to find the volume. Okay, so I call these non-circular problems or non-rotating problems. The book will talk about, he said at the beginning, these are the very first problems, actually in the book, they'll say it's like general slicing method is what they call it. general slicing method. So when you do the homework, recognize the first ones you're going to get, I'm pretty sure, are this general slicing method. Okay, let me give you an example so you can see exactly what this would look like. Once again, you start with equations to define the shape. This is first quadrant. So you graph it. And you put in 0 and you get 2. So 1, 2, 1, 2, 3, 4. So here is your first starting shape right here. And the directions will go something like this. They'll say, that's the base. And now something's sticking out. And when you cut it, and they'll say either perpendicular to the x or y axis. So here we're going to cut perpendicular to x-axis. In other words, they're telling you this is a dx problem because you're going to cut perpendicular. You're going to cut it like this. And then they're going to tell you the cross section. The area, what it looks like, in other words. In this one, they tell you it's squares. So you cut it, and when you're done, and you lay the cheese on the counter, every piece is a square. Like, how do you visualize? It's so hard for people to visualize. It would be as if, like, if I'm cutting a piece out of here, here's a square. So this thing ends up looking like this. It's kind of hard to even draw on here. So all of these pieces are squares being cut out of it. Okay? So, but it's not really just a square, it's got a thickness to it. What's the thickness? dx. So every single problem, it doesn't matter what the cross-section is, the volume of that piece is always the area of the base and by base we mean the cross-section times the height. And just hold on a second. The height is delta x always. So these problems, I think, actually well, they can be pretty tricky, but at least you always know the volume is equal to the integral from A to B of the area of the cross-section and that's it. And they'll tell you what the cross-section is. For this problem, the cross-section is squares. So the area of a square we know is the side squared. Do I have any pi here at all? No, because pi was in when you had a circle. Pi r squared. This is a square. I've seen triangles. I've seen trapezoids. I've seen semicircles. I've seen a lot of different shapes. You just have to know it's the integral of the area of that cross-section. Again, from A to B. So to do this problem, the x values from the beginning to the end, when you look at your graph, they would be, as you can see, 0 to 4. The side of one of these squares, well, that's just this length right here. This cut, that's the side, that's the base. That's S. Well, that's top minus bottom. So it's your equation, the square root of 4 minus x minus 0. So that's what the side would look like, that function. You would plug that in for S. And it's the side squared. And that's what you would do. And again, it all comes down to the cross-section. You just have to be ready to be able to find the formula for the area of that cross-section. Here is your assignment. After you're done going over the homework, you're going to have time to work on this. And then we will go over it on Friday. This is number 20.
So if it's really long, it's supposed to be easy, right?
That doesn't look too long to me. to focus on one thing at a time because it is hard.